Hi everyone, good afternoon, good morning. Hopefully you can hear me properly. Don't hesitate to just tell me if you're listening for me properly. And if you can see me, I'm still arranging some of the setups. Trying to optimize the monitor I'm going to share with you. And things are not always going as smoothly as we'd like. Hi Warren, hi Tonga. Thank you for your feedback. I'm still waiting for my secondary monitor to react, but I'm not sure why it's not really reacting. There we are. So that will give 1 or more minutes for more people to join if necessary. And I'm just going to change. Okay, this sharing screen and show the other one. Is this better with the mic now? All right, so let's get started then. All right, guys, sorry for your patience with these these tiny technical issues with the start, but now we're getting started. So thank you for joining this webinar for the second session of the day. So most of you guys will be from Europe and maybe Americas probably. So welcome in this session. Among these series of webinar, we would like to introduce you today with a specific workflow that I would like to show. It's kind of an original workflow, and you're going to see that it's in combination with Udomore, developed by Seisquare. So some of the members of Seisquare are here today. So during this session, if you've got some thorough questions about what I'm going to present about the Udomore part, don't hesitate. Some knowledgeable people around the corner here in this session. So this session is called Assessing Trap Uncertainty, and the workflow we want to present as a geological and stochastic workflow for early exploration. So it combines some geological modeling first inside PaleoScan, and then we're going to switch for statistical assessment of the traps inside Udomore. So let's start with a few slides. So this global presentation is going to last for about 40 minutes, and then we're going to have about 10 minutes for questions if you've got some. So I cannot hear you, so don't hesitate to leave your questions within the chat. I'll answer them in the end. And I'll start with a few slides then, and after the slides, we're going to dive into PaleoScan and Udomore for some concrete examples about what I'm about to show now. So the plot of this presentation is that, of course, no matter if you're in conventional exploration workflow or if you're in CO2 injection projects, then quite early in the workflow, you need to get to know the structure of your potential traps of your reservoir. So here we've got a configuration where we have a reservoir, mostly in blue here. And because of many levels of uncertainty, then you always have some unknown about the position, the actual position of the top and the bottom of your reservoir. So here you've got some tiny gray dashed lines that would represent the P10 and P90 of the potential position of these top and bottoms. And depending on the scenario, you'd see it like here, you would have significantly variable amount of gross rock volumes into your system. Okay, so scenario can be very different. So it's important to manage this. Here is another example of strictly the same situation, but it's an example where we like to inject CO2 into a reservoir. And similarly, so the same P10 and P90. And another scenario here where you see that actually here the structural traps involved in here will be a bit higher than potentially be initially considered, depending on the scenario. So all this to say that the uncertainty has to be managed right from the exploration workflow to assess your potential traps. And we're going to have a quick review of what the main uncertainties may be. All right, so as uncertainties, maybe one first uncertainty would be linked to the mark position, so to the definition of where the marker is going to be. Whenever you're logging or getting like your instrument down the borehole, then you may have some error in there, and maybe a gap or a glitch in the actual real position of the formation top you're targeting, and that has to be accounted for. Then the second error would be directly derived from the interpretation of your reflectors into well travel time, due to the thickness of the reflectors, to the definition of your seismic. And then from this, you can map some uncertainty maps on the horizon, such as this one. And finally, if you want to go towards GRV, so gross rock volumes, then you need to depth convert your volume. And to depth convert your volume, you're going to need a velocity model. So this is what is being shown here to the right. And no matter the type of velocity you're using, you will necessarily have an uncertainty linked to this velocity. So here, for example, we've been using some constant or linear values, and in every case, there is an uncertainty associated to the constant values or to some coefficients inside these velocity laws. So this also has to be reflected in the end in your trap. So to illustrate this, here's a slide where you show a tiny video of a horizon. So it's twice the same horizon on top and at the bottom. So on the top, you see really the topography with color codes. At the bottom, you see the same horizon, but with the involved structural traps, with the closures in red. Okay, these closures are bounded by the spill points for each local closures. And you see that depending on the morphology of the horizon, it's always the same horizon, but just including the potential uncertainties we mentioned just before, then the scenario of closure are completely different. So this would have to be accounted for. So in this presentation, here is the workflow that we're going to propose. So there is a part of the workflow that is going to be in time, another part in depth. And the first part of the workflow would be in PaleoScan. I'm just going to summarize this here so that you can understand better what I'm showing in PaleoScan and Udomore just after. So the first part of the workflow here, I mean, regular users of PaleoScan are just familiar with this. This is the classic workflow that most of the user would be following. it starts all with the seismic volume that you input into PaleoScan. You can potentially condition it if you want, and then you can also import some faults, so you can pick them yourselves into PaleoScan, either manually or with some automatized techniques. And then you're going to build what we call a model grid in PaleoScan. The model grid is going to be the framework for the automatic tracking of the reflectors inside the entire seismic volume. This model grid is constrained by the structural structures that are inside the seismic volume, so faults, and it can be manually refined by the user in case needs be. And from this entirely propagated seismic volume, we provide PaleoScan with a geometrical constraint that is going to actually help building what we call the relative geological time model. So the relative geological time model is this tiny color cube that captures the whole geometry of the sedimentary deposits. And from this type of model, we can derive a variety of items in PaleoScan, but in particular, we're going to be able to derive in the example here a top and the bottom horizon for like an explored reservoir, an explored level, stratigraphic level. All right. So when we have this, by using a velocity model, you can build a velocity model in PaleoScan. You can also import some velocity cubes if you want. Then you can depth convert these horizons, right? So you've got structural highs in there, and if you combine it with some structural attributes or some attributes mapping, not necessarily structural actually, such as the one displayed here, which is the RMS amplitude, then you can determine the lateral extent of potential anomalies that would correspond to hydrocarbon accumulations. So the structures correlated with these anomalies would help you create in PaleoScan some geobodies that would correspond to a specific gross rock volume. In this case, the issue is, or the limitation is, that we only create one scenario, a deterministic scenario, and that's it. And then we stop here. You have to manage this, and you don't have anything about the uncertainty here. So to kind of circumvent this is where we're using Udomore here. And what we're going to do inside Udomore, we're going to transfer some specific items to Udomore. So we've been starting to develop the transfer of items between PaleoScan and Udomore. So in particular, we're going to need the horizons, and also the seismic volume, okay, the volume that includes the amplitude of the seismic. With an amplitude, volume, and a horizon intersecting this volume, Udomore is able to work out some uncertainty map for the peaking interval travel time of this horizon. And this is what is actually symbolized here with this tiny horizon map. You see that some values have been, some uncertainty values have been mapped. And if you combine it with the uncertainties that you have on your velocity model, also the uncertainties that you have on the position of the markers, then you're going to be able to simulate stochastically a certain number of counts, as many scenarios for one given horizon. So let's say, for example, the horizon, which is the top of your reservoir. So I can run 10 simulation and end up with 10 scenarios for the top of the reservoir. And each of these scenarios will have a different topography. And as a result, the location or the extent of the closures, which is here highlighted in red, would be different for each simulation count. So to better illustrate this, I'm showing this cross-section here, where you can see like the result of 100 simulations, let's say, okay, where we've accounted for all these cumulated uncertainties here. And we see that we've got a very small uncertainty at the well location, of course, at the marker location for this horizon, and the uncertainty is going to increase further away from the markers, from the well trajectories. In black intersection here and thick intersection, those are respectively the P10 average and P90 of the simulation. So it gives you an idea of where most of the more say probable scenario are going to be located in between this. Just to make sure we're clear on this, I'm showing through this slide the same thing. So we're starting from horizon that is interpreted in time. Then we're depth converting and simulating at the same time, taking into account the uncertainty. So we've got a series of scenarios for the same horizon in depth in here. And because of this, then we're ending up with as many scenarios of closures as we have the horizon in depth that we end up with. Okay, and because of all these potential results, then we're able to create a statistical map of the closures and then create a mean thickness map for different structural traps in a given area. And for each structural trap, then we're able to create these plots that you see here that are just a probabilistic distribution of the gross rock volume for each trap on the map. Right, to wrap things up with the slide part of this presentation, okay, you can, on top of having this scenario, use again what PaleoScan is able to create, so map some attributes and some anomalies on your surfaces. And these anomalies can be used to constrain the validity of these scenarios, so the extent of the closure areas, because if there is no anomaly at some point, you're going to be able to tell Udomore, then, okay, if the closure is reaching this area, so for example here, then actually the scenario is not valid because I see no anomaly in this location, so probably I don't want to consider this scenario. In which case, Udomore is going to be able to discard all the scenarios of closures that are going up or as far as the outside points. With this, we're able to create a statistical mapping of the closure and derive eventually the probabilistic gross rock volumes for one given trap. Okay, structural trap. We're calling structural traps in here. So now I'm going to jump into PaleoScan just to show you an example that we've been running on a real project. So this is here a project on the block of Poseidon. Poseidon is being offshore northwest Australia. So on the map, you recognize the coastlines of Australia. And then I'm going to approach this data set that is here. I'm going to cross navigate to this position so that it's going to be more easy for me to navigate. If PaleoScan agrees with me, because currently it's just getting frozen. I'm not sure why I cannot zoom in anymore. So we're going to see what happens, a bit of suspense. It's a real-time show, so we're going to see. Maybe it may just close, or maybe I'll have to kill it the hard way. Right, I'm going to reopen PaleoScan, but just in case, what you should be able to see here, basically this is the outline of the seismic cube that we're having in the dark area here. And the plenty amounts of items that you can maybe see through this are faults that we've been interpreting throughout the data. So there are plenty of faults. So this is why you are able actually to visualize the area of the data. And I think I'll have to no choice but to kill PaleoScan now and reopen. So I'm going to share my screen as soon as PaleoScan pops up again. Should be quite quick. And the second thing I would like to show you in PaleoScan is the geological context that we've been going through. Okay, so here we are, just going to reopen the session. Oh, no more session in this project. Where are we now? Sorry, it's not the right project. PaleoScan has retained another project I've been using in between. That's the one we want. It gives me some time to get a sip of water. It's good for me. I'm talking a lot. All right, so here we are. So here we're showing an arbitrary line that follows the trajectory of different wells that we have access to for this area. I didn't display the name, but you may recognize some of them. And basically what you can see here is for the geological edges, you see that the reservoir that we're targeting, which is, by the way, the yellow overlay in here, is going to be located inside the Jurassic formations in here. If I'm just changing the blending, that's the results of the geomodel we've been creating. So if you remember the workflow I showed you in the slide, there is a moment where we build a model grid. This is where we refine the geometry that is going to be used for the creation of the real the RGT model. And this is from this RGT model that we are deriving the top and bottom horizon that are making our reservoirs in yellow here. So just as a disclaimer, the geometry of our geomodel should be improved, refined at the bottom of the Jurassic here. By the way, the formation that is displayed, the reservoir that is displayed, is inside the Plover formation, for those who are knowledgeable about this area. So it's not super precise at the bottom of the section, but it will not have any impact for what I want to show you today. One more thing I want to show you. Okay, these are the top and the bottom of the reservoirs in the 3D viewer in time domain for now. We're still going to be in time. And here we are. So you see the different wells, and you've got the name of these wells. You've got the bottom and top reservoir in the Plover formation over here. So you recognize the different structural heights that we have. And for this demonstration, we're going to have two phases, two different things that we want to achieve. The first phase of analysis, or appraisal, is going to concern this area here, which is on the spine, or this sort of a crest on the upthrown part of these major normal faults, where you've got a series of wells that have been drilled, exploration wells. We know that there are some gas shows at these locations, and what we're going to try to do in this first phase is to anticipate on the extent of the potential closure and then the size of the potential traps in this location, in the Plover formation. Then in the second stage, we're going to try to look at some potential new prospects in an area that is more to the east of the area here, in an above formation, just above the Plover formation, which is the Montara formation. So stratigraphically, that's just the next one above, because there are some indications in the seismic signal that there may be some leakage through this upper layer. I will show you these images a bit after. But let's start with the first phase. So we are at the end of the workflow inside PaleoScan. So we've been interpreting a model, we've been deriving the horizons, two horizons for the top and the bottom reservoirs that are consistent with the geometry of the geology. And now we want to go into Udomore. So for this, in PaleoScan, concretely, you'll have to find these horizons into your database. For example, my horizons are bottom reservoir here and top reservoir here. I'll right-click here, and in the context menu, I'll have access to some specific options to push the Z value, so the topography of these horizons, towards Udomore. Alternatively, you could also push the data that is mapped on these horizons. So if, for example, you've mapped some velocity data, it can be useful to use the second option. But just for this case here, we're going to use the first option. So I'm clicking here. I'm going to send these data in a clipboard. And then I'm going to use Udomore. So currently I'm accessing it from a plugin from Petrel, but Udomore also exists as a standalone version. And here, so this is an existing project, it's a bit crowded. So just so that you understand how it works, I'm just going to create a separate workbench in here that is a bit devoid of any table. And what I'm going to do, I'm going to display the database of Udomore, so that we call it Udomore workshop. Here we are. you have the feeling that there are already plenty of things in here, and that's the case because I told you it's an existing product, so there are plenty of things. But what I want to work on is this workbench, and I'm just going to call it webinar example, so that we know what it refers to, and then I can close this. Then what I will do, I will create some repositories where I'm going to store the different elements I'm going to need for this workflow, okay, that I will get from PaleoScan. So that's one first repository, but I want to rename it Horizons, for instance. Okay, and then I can close this this thing, and I'll right-click on this repository, and now I'll just pull the horizons that are currently in the clipboard at this location. By default, if there are several horizons pulled at the same time, they're going to be inside one particular folder, but I can relocate them like this. Sorry. Inside a main folder, and I'm going to delete this one. Okay, so I can do the same thing for cultures. For example, I'm going to need this a bit later, so I'll create a second repository for the cultures. Cultures are going to be used to host. Sorry, I shouldn't have created this at this level. Yes. So the cultures are going to hold the default information to indicate later on in the workflow to Udomore if some fluid should go across the fault according to specific column, fluid column. Okay, and I'm going to call it culture. Or polylines, I could have called it polyline, which is a bit more general maybe. All right, and I've got this. So when I got all my items, so I could import also the markers and other things, but I'm just going to save a bit of time and just show you this. What I'm going to do is to create what we call the workstation, in which I'm going to be able to build my workflow inside Udomore. So the first brick that I am going to need to perform here, if you remember my first slide, is the create a horizon uncertainty map. Okay, so I'm putting the horizon uncertainty box in here. And if I want to have more detail about this engine, then I'm going to double click on the box itself, and it's going to open the interface to calibrate my inputs. So in this example here, to work out the uncertainty, I'm going to need the seismic amplitude volume, like I said before. I'm not going to drop it here, but this is what is required in this top field here. And then I'm going to need to assign my interpreted horizons in this table down there. So for example, I can take my reservoir top, I can drag and drop, I can add another line for the bottom, all right, bottom reservoir. And in reality, I could also include more horizons that would correspond to boundaries between stratigraphic intervals defined by specific interval velocities, right? If in my data set I've got some density and sonic data, it's going to be interesting for me to use the, for example, the interval velocities. And so I'm going to have to assign some specific velocities per interval, per layer. And these velocities are going to be actually reflected as a mapping on some boundaries in between these interfaces, in between these layers on these stratigraphic intervals. So I could add more lines where I would put more of these boundaries in there. Just a quick look at the outputs that Udomore is going to derive in here. So if the lateral resolution or the orientation of the seismic cube is different from the definition of the surface itself or the horizon itself, then Udomore is going to produce something rescaled. And in particular, what we're interested in here, I'm going to simplify thing, is the sigma, which is the uncertainty on the horizon. So we're going to create a map of uncertainty on each of the horizons in this table. So a second brick here would be the depth conversion brick, because we need to convert in depth. So I'm going to add up another brick here, the depth. I can also have a look at it just to see how it's what it's made of. So that's the interface for the depth. Again, I've got a table here where I'll have to drop again all my horizons. So the top and the bottom of my reservoir in particular, but also all the boundaries of the layers that are above. Okay. all the boundaries between the specific stratigraphic intervals with the interval velocities. So as many as I need. Then in the second column, I'm going to have to enter what we call a marker set. So it's a series of points or markers that are associated to each of these horizons. Okay, I don't have, I didn't import any right now, but this is what I should be doing here. In the velocity column, then I will have to define the velocity that I want for the layer that is just above the horizon here and in between the next one just above. So different type of velocities that you can input, just a constant or something more subtle, like for example, V0 kz. And for each of the velocity load that you'll input, you'll have to also assign a specific uncertainty. So one for the V0 here, one for the K, and etc., etc. Right, so I'd have to do this for everything. And in the end, in the output, here I've got, of course, per horizon, an estimated depth, which is the result for the deterministic conversion in depth. But in particular, I'm going to be able to check a box here that is going to create a series of horizons, accounting for all the errors that we mentioned. So the marker position, the velocity low, and the uncertainty map, for instance, of each of these surfaces, of each of these horizons. So we're going to create a series of horizons here. The number of horizons in the series is going to depend on the number of counts in the simulation. That has to be set here. So by default, it's 3, but I could put it to 10, 100, depending on the definition, the statistics that I need. Okay, so I'm not going to go further for this interface. That's basically how it works. Next, when I'm ending up with the depth converted horizons, with per horizon a series of scenarios, as many scenarios as number of counts in the simulation, I will need to obtain to work out the different stratigraphic closures of these scenarios. So I'm going to use another engine here, which is the spill module. Let's have a look at what's in there. I'm trying to double click to open it. All right, here we are. So again, here we've got a trap top, trap base, which are the top and bottom of the reservoir that I'm looking for. But instead of inputting one single horizons here, what Udomore is made for is just to input a list, a series of horizons, right? Which is going to be the result of the simulation. We're going to do the same for the base horizon. I'm going to need to input the appropriate inputs in there. Of course, I didn't calculate the step before, so I cannot input things right now. You can also include some faults, right? So I was saying before, the faults is what is determining if you want to create some leakage or not across the faults. By the way, I'm just going back to PaleoScan once again to transfer faults, just to give you another example. So here, this is not strictly speaking a fault I'm going to transfer, but rather a culture or a polyline in general. So let's say this one here. I'm going to push it to Udomore clipboard. So again, in the context menu, I've got this option. And return to Udomore. And because I created the polyline folder here, I'm just going to pull this polyline in here. Right. So by the way, if you want to visualize your reservoir here, the top reservoir, you can. And if I want to display the polyline on top, then I can as well, right? In this case, I've transferred top reservoir that is that some gaps in here because of the actual fault polygons in my horizon in PaleoScan. The best would be here to interpolate it before transferring it into Udomore, because each gap is going to trigger a leakage. And to compensate this, then I'm using some polylines here that are going to act as boundaries for leakage. And this is also the same fault set that I can input in the spill module at this point. And then if I'm using some fault set, I've got some seal parameters that I can adjust. So for example, the maximum column before there is a percolation and leakage for the fault. You can assign a constant in this field. There are all other optional parameters I'm not going to talk about. But in the end, you will end up with a spill depth, a series of horizon spill depth, spill closure. That is also going to be very important. We want this output. and other parameters that will be optional. Ultimately, the last stage I'm going to show you is the volume analysis, because you need to get gross rock volume information in the end. So we're going to have to go through this step. Okay, I'm keeping the workflow quite simple so that you can understand the basics of things in here. We could make it more complex, more robust, more like with different variations, but let's keep it simple for now. This interface looks like the previous. So again, you'll have to re-enter the top and the base of the reservoir. Again, you would choose some lists in here. Sorry, the lists are here. Okay, so this is what this icon represents. You'd have the lower contact if you have some. You'd have the region, you got insight. So insight will be the point. Remember, for the first phase that I wanted to show you, the insight points are the points along all the well trajectory where there is one gas show, right? We know at this point there is a gas show or a hydrocarbon show. So this is what these insight points are. So again, there would be points that I would have to store in my database. I don't have them here, but this is what I should include here. And then I'm just looking at the reservoir base, upper contact. I think that's the region here that should include, no, that's not the region. I've got a doubt about it, but yeah, probably upper contact, where I should input the spill closure just to make sure I'm computing the volume where there is actually one spill, so where the traps are. I'll check at this in the next part because I've got some real examples to show you in these other tabs that are down there. All right, and then you're ending up with so the mean thickness maps in here. You're ending up with, in particular, the gross rock volume information in your region here. So one last thing before I show you the real data behind the scene. What is very interesting in Udomore is that you can batch all these steps of the workflow, you know, by linking the steps like this, so that in the end you can just change one input somewhere and just rerun the whole workflow all at a time. And you're not obliged to go manually and run each engine at a time. Just go and have the whole bunch of outputs just directly. All right, so for some real data, I'll go into the depth conversion tab that I have here. So this is where you start to freak out because there is many information in here. I'm just checking at the time. Okay, it's fine. All right, so here is horizon uncertainty module that is open here with some real data that has been inputted in here. So this time you see that there is an amplitude seismic cube that has been inputted. You see that there is a series of horizons here. Again, these horizons correspond to the boundaries of the layers having a specific interval velocities, down to the top and the bottom of the reservoirs that are the two latest rows of this table. And each time, if I'm looking at the type of output, then I want in particular the sigma information here. This is what matters at this point. So with this, I'm ending up with a series of uncertainty mapping on each of these horizons that I will be able to reuse in a next step. So I'm just going to put it back just to show you this depth conversion. Where is it? Don't remember where I put it into my list. There are so many things in here, but I suppose it's okay. I mean, yeah, depth conversion, that's in here. Horizon uncertainty. I just wanted to show you the output. So all these sorts of yellowish boxes are actually containing the outputs of my of this first module here. So you have to keep being organized because you're going to generate like plenty of outputs potentially here. Okay, the second step, remember, this is the depth conversion. This is also where we're going to go through the simulation to account for the uncertainty. So in here, again, you see the same series of horizons that you've seen before. This time, there are some markers associated to each of these horizons. There is an uncertainty associated to these markers. The uncertainty would tend to grow as we are going deeper in the seismic section. Then there is a seismic velocity law in the next column. Again, there is an uncertainty on all the parameters. A parameter here, if I'm using the A times V seismic for this. And there is an output type. So you see that the seismic velocity may vary depending on the interval I'm considering here. And do not forget, in particular, for the top and bottom reservoirs, again, they are the two latest rows in the table. in terms of output, you have to check here the simulated depth, because you want the many scenarios outputted from the simulation to be created. So we've got to create this series of horizon per for the top and for the bottom horizons. Here I've probably run like 100 simulation, and I've got a series of output that are here. When this is done, Udomore is also calculating a velocity model, and the velocity model that you're calculating is going to be actually calibrated with the real data you're providing to the software here. So you're having a priori velocity laws. You've got some uncertainties on your velocities. These uncertainties are, by the way, reflected on these points, on these dots that you see here. This is the vertical bar that you see here. The uncertainty on the marker position is the thickness of this bar. And Udomore is going to reuse this real world information, which is in gray, just to recalibrate your velocity to make it fits to something more consistent, which is the post-trend depth, so in orange in here. All right, so this is a way to QC your the result of your velocity model, and this determines the conversion in depth of your horizons through the simulation. So again, I've got somewhere I've got somewhere where I've got outputted all these horizons. So the next step is going for each of these top and bottom horizon to analyze the spill closure. So for the first phase, remember the first phase is just where we want to estimate the extent of the reservoirs, where we know that there is a gas show. We're going to go through these spill modules. So here there are like as many spill modules as their known gas show location, and we're going to accumulate them a bit later on in the workflow. So you see that for the trap top and trap base, we've infilled these parameters with some series of horizons, so series that are derived from the simulation for the top. Same thing for the base of the reservoir. We also included the faults, same faults that I showed you before. The inside point for Poseidon 2, that's the well Poseidon 2, but see just next to it, to the left, I've done the same for Poseidon 1, and etc., for all the other wells where there's a gas show. And then we're creating this way a table of potential closures. So this is this output that I can open. So this is a table of scenarios for the closure. And here I will open one of these scenarios randomly just to see how it looks. Here again, you've got one particular closure here in red. But if I'm looking at another one randomly, like this 115, for instance, all right, then this time you notice that the extent of the anomaly is way different. Okay, right? If I'm just setting the same scale. This is because for this top of the reservoir, when we convert it into depth, we've been using the uncertainties stochastically, and therefore, depending on the scenario, then the closure is not the same. And therefore, in this series, we've made 100 simulation counts. We've got 100 different scenarios. Right, so we're going to be able to use this to create a statistical distribution of the closure and after. Right, so this is for the spill closure, and maybe I'm just going to check these things. Just looking for a mean surface. I mean, I have one somewhere. Okay, so those are examples of averaged closures. So you see where it's red, it's near 1. Oh, sorry, these are depth maps. Sorry, I'm on the wrong information. Sorry, let me go to inside Montara. Maybe I'll have more example. Okay. Yeah, okay. So this is an example from the second phase. So it's not exactly relevant the way I'm showing it, the order I'm showing it. But this is the example of a closure for the prospect area. We're looking in the Montara formation, right? Where you see we accumulated different scenarios, and statistically, then you see the distribution of the closure here. What you see in purple, the 4 dots you see in purple around this anomaly, or this statistical closure, are the points that we define as being outside based on the anomaly of amplitude we mapped in PaleoScan with the RMS amplitude. So I'm going to show you this in PaleoScan now. I'm going to return to PaleoScan just to show you this anomaly. I'm going to reopen another session for this. So this is the anomaly we've seen in Montara. I'm going to time my windows. I'm going to adjust with a more suitable color bar. Here we are. And playing with this color bar, what I wanted to show you. So first of all, so maybe if I'm initializing this, center, where is my anomaly here? All right. All right, this is somewhere along here where we see, okay, and I have to, it's not super visible in here, so I have to switch. So you see the topography here of the top Montara formation. And you see that there's a sort of structural high where I'm having my cursor now. And I'm going to switch to the data, which is the mapped RMS amplitude in here. And yeah, this is what I wanted to show. So in the seismic section that is just underneath, what you have here, and maybe I should, decrease a bit the intensity. You've got the top of the Plover formation. So this is the reservoir we were interested in at the beginning. Okay, top and bottom in red in here. So you see that there is a sort of anomaly here, which is in a sort of a saddle point with these bright reflectors. And there is a major normal fault in here. And we suspect that there could have been a leakage from the fault and that some potential hydrocarbons have been stuck underneath this slight structural high, which is the top of the Montara formation in pink, right? And this is the anomaly that you can see around here. So again, if I'm switching back to the topography, then you see this is a slight structural high in the vicinity. Again, switching back. What we've been doing in PaleoScan, we've been saving some location points. So here, here, here that are outside the anomaly. We can also do the same thing to save inside location points. And these points are stored in here. So there are plenty of different areas of interest that we've been looking for. So there's plenty of points. And then we've been transferring these points to Udomore. Okay, so this is why, if I'm going back to Udomore, you're going to see these points outside in here. So this is what helps refining the different scenarios and discarding the scenario where the closure would reach this point, because these are scenarios that we know are not relevant. Okay. All right. So to wrap things up, I'm just going to show you how to transfer back, or we transfer back these items towards PaleoScan. It's as easy as we've been doing for the transfer in. I'm just going to try to find this information here. So for example, inside Montara, I'm going to look at the closure statistics outputs. So that's the map of closure probability. I'm just going to reopen it just to make sure it's the same I was showing before. Yes, it is. All right. So when I've located my surface I want to transfer, I just have to go for a push. I return to PaleoScan. And here I'm just going to choose where I want to put it. So for example, in here, depth, I'm going to say this time, pull Udomore clipboard, right? So PaleoScan detects that there is an incoming surface with some mapping. It knows what type of mapping it is. It says logical because it knows that the values that are mapped are ranging between 0 and 1. There's a specific type of value. And so it offers me to either map this information on the topography of an existing horizon in my PaleoScan project, or save it as a geotiff. Let's skip with the first option. And here, for example, I can map it on a horizon that I've derived from Udomore, estimated depth, okay, which is a deterministically depth converted horizon. I say yes. Okay, so the horizon is being created here. Okay, so I can open it. Open it in 3D viewer. That's not this one because, is it? No, it's not, because we should be looking at the horizon in depth. So let me switch in depth so that we can visualize it. All right, that's the one. All right, I'm going to readapt the color so that it looks nicer. All right, here is the statistical distribution of the closure for this potential prospect where there could be a leakage into the Montara formation. It's very small here, but this is what we can derive. And more for a nicer display on the previous prospect that will not the prospect that we're looking, but the extent of the known gas shows that is more around here. I'm going to show one last session before opening the questions or before having a look at the questions. Okay, so here we go. So that's these two horizons that you see are now in depth. These are the bottom and the top of the plover formation where the gas shows are being observed. So initially we start with just the topography of the top horizon here, but we've mapped, accumulating all the structural traps in this location, and we've accumulated the statistical closure of this area. So all the area in red is like where the closure is the more probable. So the redder, the more the closer from 1. And when it's blue, then there is no chance of closure. So this is what it means. This can be converted into a mean thickness map that you can see here. Okay. So when you are looking at the reddest values, you see at the corresponding column scale, you see that you've got some accumulations up to 250 meters or something like this, which is quite significant. And then for the potential leakage that are going to be more towards the southeast in here, more toward the east, inside the Montara formation, so the formation just above. All right, there we are. So again, this is a blending with 3 different channels. So this time I always have to change this display here because the color scale is not properly set. I think it's more 8, yeah, something like that. All right, so again, you see that the maximum closure is where the most red area is. It's not 100%, so there are some scenarios in which there is no closure at this position. This is what it means. Again, it can be, we can see the anomaly here, okay, that we've mapped from the time domain onto the depth domain. So you can just make sure that we're consistent with the position of our anomaly, and theoretically, this distribution of closure should avoid all the points where we've indicated there was no anomaly, so the outside point. And yeah, and this can be converted into a thickness map as well. Okay, so this is this. So you see that the maximum thickness is about 50 meters. That's not very important. And if finally I'm returning to Udomore to show you this graph, where is this graph? I've seen it before. Here we go. So in Udomore, we're able to generate some reports. And in the reports, then, okay, this is the graph I wanted to show you. This is where you have the distribution of your gross rock volume in terms of probability. So in this graph, you see that it's like the chance of having something about 1 cubic kilometer is very, very low. So actually, it's a very, very, very small prospect. But it was just for the purpose of the demonstration that we've used this, this potential prospect. And yeah, this is what we obtain. So I think this is it for me with the presentation. I've reached the end of what I wanted to show you today. I'm now going to check at the chat, see if you guys were talkative. Okay, I see that there are some questions that have been answered already, which is perfect. About correlation, can talk and base be continued with respect to the correlation errors. No. Yeah, okay, this has been returned. Okay, follow-up. No. Sorry, I'm just going through the questions again. So, Torgev, thank you for your many questions. Well, again, for everyone else, if you still have something in mind for later, don't hesitate to contact us. So at contact@eliis.fr or support@eliis.fr. We'll try to answer your questions, and we may also redirect you to Michael that was here from Seisquare, for example, so that you have more precision about Udomore. So don't worry. This session was recorded, so you'll also have the recording available. Yeah, I'm just checking for the most upcoming things. But apart from it, I'm done with this session. Thank you again for attending. Thank you for your interest. Yeah, oh, there's a question from Hector. So sorry for this. I may have missed this. I didn't see the question of Hector. May have missed this. Just checking in. Okay, maybe it's a private question or something. So sorry if I cannot see it through the chat right now. Okay. Thank you, Michael. Again, you're like burning out with your keyboard right now. So I'm not going to end up the session right now, just so that you have time to answer. No stress. Also, what we've not said is that indirectly, when we're inputting some inside points and some outside points here, then indirectly we're restructuring or refining the velocity model that Udomore is creating. So really, the velocity model that Udomore is creating is really refined with your real data and what you observe. And this is one of the original parts of this software that not everyone else is able to do. So yeah, this is very powerful. It looks a bit complex from the start, and I'm a geologist. I've been using Udomore just for a few months, so I understand this point. But behind the scene, I mean, it's there's really a potential for you to handle your data and get your uncertainty from something that is really grounded to the data. I guess, Michael, you're going to have a lot more questions. I'll pass on the question of Torge or anyone else if needed. So yeah, don't hesitate. Thanks everyone. Thanks a lot, Michael. Yeah. Again, I'll let you time to write down your questions. I'm just going to switch. Well, thank you guys again. All right. Bye-bye, everyone.